So, question 3 has many parts for the midterm. It starts off with this pretty simple question where it gives us A and then asks us just to calculate A inverse. The process for this is straightforward. All you have to do is set up an augmentation with the identity on the right and A on the left, and then row reduce. If the left-hand side doesn't row reduce the identity, then we know that A is not invertible. But if it does, we'll have the inverse of A on the right. So here I've done some row reductions, and what we get is A inverse on the right. And we can go ahead and write that out. I'll write it over here. A inverse is equal to 0, minus 1, 1, minus 1, 2, minus 1, 1, 1, minus 1. Okay, so that's A inverse. Now, if you had enough time, what you could do is you could quick check to make sure that your computations worked out right by multiplying A and A inverse. Hopefully what you'll get is the identity matrix. As long as that works out, then you're good. Assuming that both you result in this thing is square, then it works. Okay, so the next part of the question asks us to use A, and also A inverse, above, to solve for various B's. Now our first B is a B so that A times B is equal to this matrix over here. Now all we have to do to solve for this is multiply by A inverse on both sides. Once we do that, we get B is equal to A inverse times this guy here, since A times A inverse is the identity. And we just do some matrix multiplication, like this, and we get our result. Pretty straightforward. The next question is pretty similar, and we could solve it in exactly the same way by multiplying by A inverse on the left on both sides and solving for B. But another thing we can notice is that this column vector right here is actually the second column of this matrix here. So the second column of B is going to give us the, right here, will give us our answer. We can see here, this is really the formula that does it all for us. Yeah. So the next question is related to the ones we had, but instead of doing A times B, we're now doing B times A, and we have to do some solving for this. Now all we have to remember is instead of multiplying by A inverse on the left, we have to multiply by A inverse on the right, and then we can go ahead and solve for B. And it's exactly the same process, and over here we get some matrix. The next question uses B from up here. So we have this value for B, and what we want to know is what value V can we get this vector? Now we could solve this in the traditional way, where we go ahead and write an augmentation with B on the left and 1, 1, 1, 1 on the right augmentation, and go ahead and row reduce and solve for V. And I went ahead and did that here. You can see this involves a lot of work, many row operations and such. But in the end, we do get an answer, and we'll get the vector V is equal to 2, 3, 4. So it'll work, but this takes a long time. There's an alternative way to solve this. Instead of augmenting here by B, from what we solved for here, and writing this guy on the right, we can augment it, and we can write B times A on this augmentation. Do a little bit of row reduction. See, the row reduction is much more simple. And at the end, we'll get this vector W. But W is not our answer. All we know about W is that if we multiply W by B times A like this, then we get 1, 1, 1, 1. However, if we associate, we know that A times W is a vector, so that when we multiply on the right by B, it's going to give us 1, 1, 1, 1. So that means that if we let V equal A times W, which we can just compute with some matrix multiplication, then we have our answer. And you can see this is the same thing as we had before. Now there's one last part to this question. Instead of having some simple equation like b times a equals something or a times b equals something, what we have is this complicated algebraic expression we need to solve for b. To do this, we just got to manipulate the equation a little bit, rewrite it a few times, and solve for b. That's what I've done here. We have, I can multiply on the right by a inverse twice, and we get this expression. And then if I move over a inverse by subtraction, then we get b equals a inverse squared minus a inverse. We don't quite know what a inverse is yet, a inverse squared is, but we know what a inverse is. It's right up here. So just got to square a inverse to give us this matrix, and then we subtract one from the other, and that gives us our answer for b. That's it for this question. If you have any questions about this question or any comments, then please ask me in class or in the comments below. Thank you very much.